Okay, so as functional programmers, probably one of our prides and joy is the wonderful marriage we get between theory and practice, right? So we have these great ideas like the lambda calculus and natural deduction that come up from the theory of mathematics, but it turns out they're not just theoretical, they're also really great practical tool set for addressing real-world problems in programming. So for instance, they're a great basis for programming language. So all of our functional languages like Scheme, ML, and Haskell are based on the lambda calculus. But we as programmers aren't the only people to think about our programs. We also have compilers that spend a lot of time thinking about our programs while trying to come up with an executable that we can actually run. So what about them? Well, the lambda calculus itself has been used in compilers as an intermediate language for decades. And it's been a really fruitful area of research and application. But we find out that lambdas aren't the only game in town, in a sense. There's also something else that also comes from the theory. And it turns out to also be a useful intermediate language for compilers to use while compiling. This has also been explored previously by Ohori in showing that the sequent calculus can be used as a logical foundation and a way of describing some important low-level aspects of compiling. And so we're going to look at our take on this situation and where it fits in between the uses of lambda calculus that we have already in our existing tools. So to begin, let's look at how intermediate languages are used in compilers as part of the whole process. So, essentially, this is the compiler's job, right? We have two ends. At the top, we've got the source language. This is what we write our programs in, and it's a very rich language with lots of great features that we can use to easily write our programs. But at the other end, we have the machine language, which is full of details on how the calculation is to be drawn out, but doesn't have many features for someone to use. This is why we use the source language. The compiler's job is to take the program we write in the source, bring it to the machine, but if we want to, we don't just want any machine code. We want something that's reasonably performant, right? We don't want to wait forever. And to go from such a feature-rich to a detail-rich setting is a bit of a long jump to just do all at once. So we want to put something in the middle that we can use as an intermediate on the way through. And so that's where an intermediate language comes in. So one example of this is using the lambda calculus in direct style as an intermediate language. So what we do is, for instance, if we look at Haskell, there's tons of features, but really you can kind of desugar down into a very small core of the real essential features that you need to represent the computations that take place in the program. And then once you've got it at that stage, you can work on it for a while to optimize it and make the program more efficient, more performant, and more what you would write by hand. So instead of having the very nice and abstract stuff we would actually write, we get the sort of hand-tuned code practically by the compiler. And then after doing that, you can move down to the machine, generate the machine code. That's sort of a very bird's-eye view of what's going on and the parts that we're focusing in on. And so the core, as I said, is basically a lambda calculus plus a few more features, depending on what language you're working on. And the issue of evaluation strategy comes up if it's a stricter lazy language that affects what optimizations you can do, and so that has to be taken care of in your optimizer. But there's another way to use the lambda calculus, and it's also very popular. It's using a continuation passing style. In this case, we still have the same sort of desugaring process where we go down maybe into a core, but then after that, we do a transformation that removes yet another feature from our language, which are the ability to compose functions, essentially. So all we have now are tail calls, and an effect of this is baking in the evaluation strategy. So now the optimizer doesn't have to care about that, but that CPS transformation will depend on what sort of language you're starting with. So you're already introducing some additional details that you may not have thought about in the source language, especially for a pure functional language. So that's sort of the situation there. So now let's look at, in contrast between these two different uses, how does a sequent calculus, what is a sequent calculus, and what does it look like as an intermediate language? So as we know, there's not just one logic, there's many logics. And there's two particularly important ones that came out at the same time. So in the 1930s, Gensen, in the same paper, introduced two logics. One of them is natural deduction, which is probably the one we're most familiar with because it resembles our functional programming languages. And it was designed to be close to what mathematicians think, more or less. But Gensen wanted to prove that natural deduction has some really nice properties, and that was rather difficult. So he, of course, invented a totally different logic that was a lot easier for him to reason about and do the things he wanted to do. And both of these together have formed pretty much the basis for, largely the basis for logic that came after that. So these have been extremely influential. As we know, the Curry-Howard isomorphism, that tells us natural deduction, that's the same thing as lambda calculus, right? That's great. But Curry-Howard is not just a one-hit wonder. It keeps coming up over and over again. And so you might ask, well, sequent calculus, that's a logic. What kind of programming language corresponds with that? And so the one we're looking at is kind of like an abstract machine-like language. So essentially this is bifurcated in two. So you have a language with two different components, signifying the difference between left and right hand sides in the sequent calculus, or the difference between thinking about truth or false. It's a language about duality and symmetry. So on the one hand, we have producers. These are values that give results. And on the other hand, we have consumers. These are continuations that do something with that result. And the primary composition operator of the sequent calculus is a cut. This is what connects a conclusion with an assumption, or connects an input with an output. And in the language that resembles the abstract machine state, where we have a value or a computation that we're evaluating with respect to some continuation or context, is the idea there. But it's not quite as low level as most of the abstract machines we would use. It still has some nice features like binding and substitution for static variables, which makes it a lot easier to manipulate, like the lambda calculus, while still including some more details that matter for execution. And sort of the amazing consequence of this, and so the language we use is based on Corinne and Erbelin's calculus from 2000, is that in some sense, Gensen discovered statically typed call stacks way back in the 1930s before we ever had machines to run them on. Like, that's pretty amazing that it worked out that way. It's pretty great. And so now let's look at sort of the flow chart for what does a sequence-style intermediate language look like. So it's got a resemblance to the continuation passing style flow, but there's some really important key differences. So on the one hand, we've got the translation between core and the sequent core, which is the sequent calculus correspondent or counterpart to the core language, which is the lambda calculus. And that translation can easily go both ways. Right? So often in using continuation passing style, once you do the transformation into continuation passing style, you pretty much stay there the whole time. Here you really don't have to. That means you can do optimizations both at the level of the lambda calculus and at the level of, or core and at the level of sequent core, and go back and forth. The other feature is that, or the other key difference is that this translation doesn't have anything to do with the evaluation strategy, unlike the continuation passing style. So you can actually use the same translation for both strict and lazy languages. And that means that during optimization, because the evaluation strategy isn't baked in, you have more flexibility in what you do. So it's got some features of a direct style representation and some features of a continuation passing style representation. It's a bit of a compromise and a mix of the two. But what are the differences between these two representations? If we can go back and forth, why would we use one over the other? So core, as a lambda calculus, this is an expression language. It's all about expressions that return values. It's like functional programming. That's the heart of everything that's going on. In sequent core, instead, we have a dual counterpart. So there's both data flow and control flow that contrast one another. And that's the duality between giving something as an output or taking something as an input. The producer-consumer dynamic between the two. And so the point is that you can get a language with both data and control flow, but because you can translate back and forth, you don't ever lose any of the advantages of core or of the lambda calculus, right? So the two-way translation preserves both semantics and types. When you translate, the types are the same. And so you can really have the best of both worlds in this way. It was also a really important part of the way we implemented this intermediate language. And so let's move on to sort of the main thing we learned when we put this to practice in a compiler. What was the key addition that we found? And the main thing that we found is that there's this umbrella concept of continuations that shows up in continuation passing style and all sorts of other representations of control flow. We found that there's really two different roles, and that in the setting of a lazy, pure functional language, they're rather quite different. So the most common one that I think people think of when they think of continuations is continuations as evaluation contexts. So for example, here we just have a simple arithmetic expression. In a sense, we are evaluating f in a particular context. So we're calling f, the function f, giving it the argument 0, and then we're adding 1 to its result and then multiplying that by 2. This list of what we're doing to get a result out of this expression is the evaluation context. So these are things that are about doing, how to transform some intermediate result into the thing we ultimately want. That's their purpose and their role, and the most common thing that we do with continuations. But there's another thing you can do with continuations, and this, sort of comes up in imperative languages as well. And so we have this little tiny imperative script. And the whole thing here is that we're doing a conditional. We're checking some condition. We're checking if x is big, and we're going to print out whether or not it's large. So we do something different in either case. But at the end of the day, no matter what we do, we're going to come back together and print goodbye as a prompt. So that point where the branching control flow comes back together is referred to as a join point. And these are represented as phi nodes in static single assignment in representations for imperative languages. But the same thing shows up for functional languages because we also have if expressions and case expressions. The same sort of branching control flow occurs, and we have even more instances where it comes back together because we always, at the end of the day, return a result to whoever's looking at us, right? And so here, the point of join points, they're really about sharing. They're about representing the fact that this is a graph that comes back together and not a tree that goes and does potentially two different things. And that sharing is the key. It lets us, it lets us not duplicate code, which can become a really serious problem in a compiler. If you keep duplicating, you can get a terrible exponential blowup and not be able to finish compiling. So that's super important. And so, as I mentioned before, when you look at these two things in a lazy functional language, they're actually really different from one another. And trying to merge them into the same thing doesn't necessarily give you all the features that you want. Right, so, as an example, evaluation contexts take exactly one input and are strict in that input, but join points aren't. They may be parameterized over several different varying inputs, and they may not need them. They're not necessarily strict. So, these are, pretty fundamental differences. And we might also think from the perspective of a direct style representation or just a lambda calculus, but they sound a lot like functions, right? Or even said well, a join point, they can be run many times and they're inscrutable like a lambda. Well, that's exactly what lambdas are. Why not just use a lambda, right? What's the big deal? And they can be, but they're very special functions. They have very particular properties, and those are key in letting us efficiently compile them to machine code. Because really, when we're representing these as joining control back together, we really just want to do a direct jump to some block of code. We don't want all the overhead of a full-blown closure and the function call interface if we can just do a goto. That can have an impact on the performance of code, and so it's important to recognize, even if you represent them as functions, you have to recognize a difference to get good performant code at the end of the day. And so that moving on from that, that was a key part when we went to implement Sequent Core in the Glasgow Haskell compiler. So we actually implemented this as a plugin. So GHC has a really flexible and powerful plugin system that lets you essentially come up with your own. So for the optimization phase where it's working on core, you can write your own optimizations as just a function from core expressions to core expressions. So it hands you its current state of what it thinks your program is. You can do whatever you want to rewrite it and hand it back to GHC, and it says, yes, okay, that's my new program. And it lets you completely reorder and rearrange and insert and change the pipeline for how it's optimizing core. And so we used our two-way translation to essentially lift Sequent core optimizations into GHC through this plugin. So we basically did a complete change of the internal representation on how it optimizes programs without touching a line of GHC's actual code or recompiling it. And in doing this, we implemented some of, thanks to a lot of the work by Luke Marr, implemented some of the analogs of GHC's optimizations in Sequent core rather than in core, including the mighty simplifier of GHC, which is responsible for a lot of the, sort of compressing the beautiful code that comes into really performant Lambda expressions that can be compiled to efficient machine code. And there was there was a particular aspect that we found that Sequent core was subjectively better than core at representing as an intermediate language, and that was in the representation of join points. And so let's look at a particular example where in core we do something that we might not want to do, but it's a little bit different in Sequent core. So one particular optimization or rewrite that you would want to do is essentially a family of optimizations called case of case. And so I'll do sort of a simplified version of that, where what we've got is a case expression, and we want to do something with the result of that case. So in this case, we're checking the variable z. It's either going to be constructed with the a constructor and two components, or it's going to be constructed as just b. And in either case, we do one of two things. In the first case, we called j, and in the second case, we just return false. And the thing is, well, in the second case, we would return false. And we'd really like to bring the not and the false together. We'd really like to just call not with false so that we can simplify that, because then that's less work we're actually doing at runtime, and we're doing it now at compile time. So how do we do that? Well, we could push the application of not into both branches of the case. That way now, we're calling not with false, and we can just simplify that now, and that's great. But there's a problem. In the first branch, if you notice in the original program, there was a call to j, and it was a tail call. So really, that's actually a join point, and it means we can compile that more efficiently. But in the second program, it's not a tail call anymore. That means it doesn't fit the special properties, and now we've actually made the call to j much worse. And that's very bad. We don't want to do that. We don't want to ruin these join points, because that means an optimization which in one case is improving things is in the other case perhaps making things worse. And so that's something undesirable that we'd like to avoid. So using Sequent core, presented in the syntax of core for simplicity, using the two translations. So here's the same program we start with, and we still want to bring not and false together, but we don't want to ruin the tail call to j. And in Sequent core, what actually happens, the sort of natural thing to do, is instead of calling j and then returning and calling not, you actually push not into the definition of j itself. So it gets pushed into that join point, and we still can compile this as a direct jump. So that's, really, it's good. Now we've preserved these join points, and in general, Sequent core has a special support for these things, and so they're very robustly preserved through pretty much any reasonable optimization you would do, in the same sense that the Lambda calculus preserves static binding. So that's a good thing. We like that. But core knows nothing about these join points. That means that when we translate back and forth, they're totally lost, and that's bad, right? We want these efficient representations. We don't want to just lose them all. And so what we use to get around this problem of losing the join points whenever going through a round trip of translation is an optimization called Cantafication from the world of continuation passing style. This is essentially just a way of finding functions that look like join points and saying, yes, they are. And once you do that in Sequent core, they stay join points. And so this is sort of a recontification of when we had a join point, we went to core, we forgot that, we come back to Sequent core, and now we remember that, yes, that was a join point. And so it's a new application of this contification optimization. So we implemented this in GHC, and the results in terms of performance were both positive and negative. On the one hand, we ended up getting similar performance as the existing GHC optimizations that we replaced, which is, and in not very long time, which is great because those are very finely tuned over a long period of time, which means this is a feasible representation. But there wasn't a really huge improvement, so there were some occasional wins and losses. And unfortunately, the biggest cause of this was due to inlining and the way that doing these different sort of case-of-case and other transformations changes the way inlining happens very subtly when we choose when to take the definition of something and plug it into the program. And that can have either good or bad effects. It's very subtle, and it's all up to heuristics. That was sort of, any of the cases of losses were often due to some subtle interaction with inlining, preventing some other optimization from happening. And so this is a case where a more surgical modification would be helpful rather than rewriting the whole thing. It's very hard to track down the difference. There's a bunch of more stuff in the paper. If you're interested at all, I would definitely suggest checking it out. We have an extended version online with even more information. And so what was the main thing we learned from doing Sequent core? So the main thing is that this single idea of continuations actually serves two different purposes, and that's sometimes very important, especially for lazy functional languages. And that these two purposes are both very useful. So Sequent calculus is really great at representing essentially function types and working with those. And in a sense, this was something GHC already knew, because in the simplifier, you could say that on the fly, it was creating a lot of these continuations as evaluation contexts for analyzing core programs. So a lot of that was already being done in the GHC simplifier, which is why the performance was similar. And also that these join points, which are a feature of classical and not intuitionistic logic, is an important thing to is a very important thing to do for compiling even pure lazy functional languages. So I will leave it at that. Thank you very much.
Questions, please do stand up and introduce yourself. On the left, there's a question.
I'm Gleb Pergut from Google. I have a question. Your benchmarks are about the resulting code, right?
Yes.
Have you done any benchmarks of the compiler itself? Can this mechanism help with the GHC slow compilation times? It happens.
Oh, so you're asking if this would help with the completion times?
Yes.
Okay, so we don't have any evidence in that. So our implementation, like I said, was a plugin, which already comes with some slowdowns. So if we were going to really, for real, do this change, we would do it in GHC itself rather than as a plugin. And also, we use the back and forth translation a lot, like pervasively, which interestingly doesn't actually cause a ton of slowdown in and of itself, which you think it might. It's actually a pretty modest slowdown. But if you were doing this for real, you would implement more of the analysis and transformations in Sequent core to avoid translating so much. So I don't know if it would improve because we were focused on the speed of executing programs, not the compiler.
Next question. Over here on the right.
Hi, Max New from Northeastern University. So a lot of this Sequent calculus work, they have a distinction between two different types of continuations. They have like the normalized continuations, which maybe they call stacks, and then they have the ones that can compute stuff. So is that a related distinction to your two roles, or is that unrelated? And
so there is a relation. So I think what you're referring to is sort of the works on polarized languages,
yes,
both positive and negative types. So we didn't go into polarization because that wasn't really how GHC works today, and we wanted to try to keep it close so the relationship was feasible. But there is a relationship between the two. We just kind of didn't push it in that direction. So sort of the join points are more the positive style, and the other ones are the negative style, yeah.
Okay, at this point we are out of time, so we'll have to take the rest of the questions offline. So thank you very much.